Hello, everyone. So this is a special session. In these special sessions, I'm going to give a talk by picking out one specific material or the one specific topic. In this one specific topic, special sessions, I pick up the graphenes and its derivatives, and also the synthesis, the structure, and the property of the graphenes. So let's start with the band-theory graphite, which was formulated in 1947. So according to the band-theory graphite, so graphene, which is a two-dimensional nanomaterial, could not be exist because of the unstable two-dimensional material according to the unstable thermodynamically. And also, before the 1968, according to this crystalline order in two dimensions, they mentioned about it that the two-dimensional graphene nanomaterials could not be exist because of unstable thermodynamically in the two-dimensional nature. But in 1991, there was an investigation of the single-layer graphite on the PT111 planes by using the hydrocarbon decomposition process. In this research, they found that the small island of the thin single-layer graphites were found in the SD and investigation on the platinum surface. So in that case, they were so excited that to continue on the research whether the single-layer graphite, which will be in the graphenes in the future, in the present, will be named, could exist or not. And then in 1997, the scientists in Japan, they study on the thickness of the graphene crystal, the graphite crystal. The depend on the thickness of the graphite crystal, so the electrical property will be different. So they postulated that so the thickness is depend on the thin graphite crystal. The thinner the graphite crystal, the higher the resistivity of the material. And also they mentioned about that because once they try to make it thinner, the graphite crystal, there will be difference introduced in this process too. And also, they also debate that it cannot be expected that the thinner crystal have multiple or not. So there is a lot of debate in the research too. So the people keep doing about this kind of research. And in 2004, the two scientists, they win the Nobel Prize because they discovered that the existence of the two-dimensional graphenes by using the Scottish process, which is the mechanically evaluation process. They use the SOPG and then they use the Scottish process and then people the two-dimensional graphene and they study on the free effects property of the atomically thin flames. The history of the graphenes in 1947, it is not impossible. That's because of the unstable two-dimensional nanomaterial according to the band theory of graphite. And in 1991, there was observation of the single-layer graphite on the platinum surface. Then in 1997, by Japanese scientists, in 1997, 300 nanometer thin graphite layer can be prepared, and then they studied the resistivity of the thin graphites depend on the how thin of the material, and the resistivity will be varied. And 2004, so the two scientists, they prepared the few layers graphene from the highly oriented power lattice graphite, which is the SOPG, by using the Scottish process. So then talking about the graphene, so graphene have a family. So graphenes we're talking about the graphene, which is the graphite. So graphite is a three-dimensional structure. So in this three-dimensional as a graphite structure, there are many graphene layers stacked each other, bind secondary weak bonding. Then, if we can evaluate this stack layer of the graphene from the graphite, so we can get the two-dimensional graphene, which is the graphene. Then, as we blow up into zero dimensions, we can get fullerens. This is the zero-dimensional graphene, and next one is the one-dimensional graphene, which is the nanotubes. So this is the family of the graphenes. So talking about the graphene, so the graphene is coming from what? Is graphene is made of what? So talking about the graphene is a big carbon compound, carbon molecule. So carbons have a 4 billion electrons in the atomic shell. So 2 electrons in the 2s state and 2 electrons in the 2p state. But the graphene structure is the honeycomb lattice structure. So when the carbon atom is found, 3 covalent bonds to the 3 neighbors carbon atom. So this is the sp hybridization process. So in this case, to occur the hybridization process, 1 electron from the 2s state is going up to the 2p state. Thus, there will be hybridization process between up state and p state, which is the sp hybridization process. Then, as you know, the graphene, which is once carbon atom found the 3 covalent bonds, so 3 electrons will found the covalent bonds with the 3 neighbors carbon atom. In that case, there will be one electron will be delocalized, which means 1 electron will not be found covalent bonds. In that case, it's found by bonding between 1 carbon and 1 carbon. So these electrons are moving freely on the plane of the graphenes. So the electron is giving the special electronic structure of the graphenes. Here you can see the conventional band structure of the normal material, conventional material is a parabolic nature. So that means the movement of the electrons, the flow of the electron is depend on the mass of the electrons. But here in the graphene's band structure, so energy and the velocity are directly proportional to each other. So that's why we call the massless transport the graphene transport. And also, the condension band and valence band attach each other in 6 valence zones. So this is a very special feature of the graphene. These electronic band structure of the graphenes can be p-tied, can be n-tied too. We can control, we can engineer the band structure of the graphene by various factors. Not just about the electronic structure of the graphene, but also the other factor, such as atomic thickness, which is the one layer, single layer. So that's why very thin nature of the graphene. And also electromobility, which is coming from the localized electron and mass transfer for the highest electromobility of the electronic material. And also the strength is coming from the covalent bonds between the carbon atom. That's why this is a very strong, stronger than the steel. And also they have a high toughness, structurability, and also the highly good stiffness too. Because the one layer, they are very high surface area. The highest surface area that you could that's cover the entire source of fee with less than 3 grams of the graphene. So this is very special. And also high transparency, just only 2.3% of the light was absorbed by the graphene. So 97% was transparent, and also high thermal conductivity and the low electrical resistivity. Okay, now we know about the family of the graphenes. It's time for the durability of the graphene. So the graphene have the many derivatives. So we have the graphenes, we have the graphene oxide, we have the radiographene oxide. Well, the difference is that, okay, the graphenes, so in the one derivative of the graphene is the derivative, the graphene. So in these derivatives, so there is no functional groups, the very highest quality, no difference half area graphenes. This is coming from the CVD grow graphene. And later I will tell you about what does CVD mean. The next one is the graphene oxide. In the graphene oxide, you can see they have a lot of oxygen-containing functional groups such as hydroxy groups, carboxy group, epoxy group. There are a lot of the functional groups contained in the graphene oxide. Then the radiographene oxide, which is coming from the reduction of the graphene oxides to the radiographene oxide. In that case, they have a few oxygen-containing functional groups in the radiographene oxides, and also the difference that was introduced as from the oxidation of the graphite from the graphene oxides. So this is the difference in the chemical structure of the derivative of the graphenes. What about the electronics structure? Depend on graphene oxide, and graphene oxide. So in the graphene oxide, conduction band and valence band touch each other. But in the graphene oxide, the band gap is quite big. It's coming from what? It's coming from the functional groups. When we remove the functional groups from the graphene oxide to the graphene oxide, the band gap is getting smaller. So by controlling the functional groups or the graphenes surface, so we can control the bandgap of the graphene's derivative. So that is the beauty of these graphene's derivatives. So there were so many process that we could use for the synthesis of graphenes. So as you know, the graphenes, which is a two-dimensional nanomaterial. So nanomaterial, we know we have the top-down and bottom approach. The first one is the top-down approach. So the top-down approach means it's coming from the very big side of the material and then trying to decrease or separate into small scale in the range of the nanometer. So in that case, we're going to use the graphite, and then we have a three technique to prepare the graphenes like material by using top-down approach: oxidation evaluations, micromechanical cleavage, and the liquid phase evaluations. So this is the three different techniques that we can use for the top-down approach. And the bottom approach, it means starting from the one atom by atom, and we build up into the structure of the graphenes. So this is the bottom approach. In this case, we have the CVD process, chemical vapor deposition process, is the main process that we are using in the bottom end. So in the synthesis of the graphene, there will be two main techniques that's widely used in this current research. That's what we are going to talk in a little bit more detail about how these preparation of the top-down and bottom approach using the synthesis of the graphene. Okay, so the first ones in the top-down approach, we're going to use the oxidation evaluation, and then we will synthesize graphene oxide. And the second in the bottom approach, we're going to use chemical vapor deposition process, and then we will synthesize the graphene. So let's start with the oxidation evaluation process in the top-down approach. So in the preparation of the graphene oxide, we have a three principle. So for the preparation of the graphene oxide, which means we're going to oxidize from the graphite to the graphite oxides. So we have the both the methods, and in the 1860 and 1898, there is another method. In 1958, we have the hammer method. So in this day, the hammer method is widely used oxidation process from the graphite to the graphite oxides. Then people are using these hammer methods, and then they modify the hammer methods by introducing longer oxidation process, higher purification process, and they use the graphite oxides. After that, after we prepare the graphite oxides, we use the sonication process to produce the graphene oxide. In this case, these stack layer of the graphenes was going to separate by using the sonication process. And then we got the very strong yellowish color of the graphene oxides after we sonications of the graphite oxide to the graphene oxides. So after we got the graphene oxides, we're going to do the reduction of the graphene oxide to the reduced graphene oxide. In that case, there are three main techniques that we can use to do the reductions of the graphene oxide to the reduced graphene oxide: in terms of thermally, in terms of electrochemically, in terms of the chemical reductions. So for the chemical reduction, we can use the hydroxyl monohydrates to do the reduction of the graphene oxides to the reduced graphene oxide. And then in this reduction process, the oxygen-containing functional group from the graphene oxide will going to remove, and thus we will got the reduced graphene oxide. There is just only a few oxygen-containing functional group will remains on the surface of the reduced graphene oxide, and the color of the graphene oxide will change into the blood color to the reduced graphene oxide color, which is very dark black color. So this is actually an image of the reduced graphene oxides. The next one is a bottom approach. In the bottom approach, so we're going mainly use the chemical vapor deposition process. So even in the names, so we're going to use the vaporized chemical gas, precursor gas, and then these chemical vapor gas was going to deposit in one specific environment and in one specific substrate material. So deposition method in which substrate will be exported with one or more volatile precursor react and decompose on the substrate surface to produce the desired deposit. So in the preparation of the graphene, so we are going to use this chamber. Okay, in this chamber, we're going to introduce the gas inside here, and then there will be the high temperature. So these gas will be hydrogen gas, these gas will be methane gas, carbon-rich gas. So the hydrocarbon gas will be decomposed into the hydrogens and carbons in this high temperature and then in this one specific pressure. And the hydrocarbons, decomposed hydrocarbon, was going to be hydrogens and carbon, and the carbon will be deposited onto this substrate material, and then the byproduct was going to release out from this chamber. So this is a very simple process. So in this chemical vapor deposition process, there are three main stage that we need to understand. The first one is after we put the substrate into this chamber, we have to do the annealing process. So that temperature will be increased at one specific temperature. At the same time, we're going to backfill with our hydrogen and heating us. The reason in giving the backfilling is that is because of the giving the inert atmospheric environments, inert environments for that substrate not to react with the other gas that will be within the environments. So in the annealing of the substrate, after annealing of substrates, so this is also the initiations, the driving energy for the surface of the substrate too. After that, we're going to introduce this methane gas at one specific temperature, and then this methane gas will going to decompose into the hydrogen and the carbon, and the carbon will be deposited onto the substrates, and then we cool it down as slowly depend on the protocol, depend on the process that we is going to deposit of the graphenes on the substrates. So here there is so many different important parameters that we need to emphasize. So the first one is temperature, the second one is the pressure, and also the flow of the gas, what's kind of the hydrocarbon gas, methane, ethane, and also what's kind of the other catalyst like the hydrogens, argons, oxygens was going to be used in this CVD process or not. So here in this case, I just only want to emphasize on one parameter, which is the substrates, metal substrate. Depending on the metal substrate, the growth of the graphene will be different. The mechanism is very important. So the first one I'm going to tell you the nickel substrates using in the CVD process. So the first one, the nickel substrate was going to put into the chamber, then the hydrocarbon gas will going to introduce, and the hydrocarbon gas will be decomposed into the hydrogen and carbon. Then this at that stage is okay, but after hydrocarbon is decomposed, these carbon will dissolve into the nickel fin and form the solid solutions. Then there will be diffusion of the carbons from the nickel carbon solid solutions, and then the carbon will be precipitated on the surface of the nickel. This is the mechanism of the formation of the graphenes found on the nickel substrates. But what about the copper substrates? In the copper substrate, you have the same until the stage of the decomposition hydrocarbon. But for the stage of the copper substrates, there will be nucleation of the graphene on the surface of the copper, not dissolved into in the copper substrates. There was this is because of the crystal structure different on the copper or nickel. That is more to study as a very interesting thing. So here I will shove into cap that they have only formation, the nucleation of the graphene or the sulfate or the copper substrate. Then the nucleation of the graphenes will be expanded until the whole sulfate or the copper will be carbon. And then there will be termination of the growth once this whole sulfate was fully carbon. So this is the mechanism found formation of the graphene on the copper substrate. So that's we call the diffusive growth. So after we got so these graphene, so we need to understand what kind of state of the graphene repeated so we can get it. It is in the state of the graphene oxide, it is in the state of radiographene oxide, or in the state of the graphene. What is the quality of the graphene? So the graphene oxides, so they have is a lot of oxygen connected functional group on the surface of the graphene. So we can see that the hydroxy groups and carboxy groups that we can see. So the piece coming from this kind of oxygen containing functional group in the graphene oxides. But with graphene oxide, there will be one strong P that we can see, which is coming from the carbons covalent bonding. But there have a few P's that's coming from the small number of the oxygen containing functional group. But in the graphene, that we can see very clearly that only one piece, which is coming from just only the carbon bonding energy. So in that scale, we can use the HPS to understand what the quality and what is the functional good that's what's found on the surface of the graphene. So this is the how we can use the HPR. The second one, we can also use the Raman spectroscopy. This is very good, the quality of the graphene material. So the graphenes, they are with the two bands, we can see D band and G band. So to put it simply, so these for the graphene, high quality graphene, so D band and G band is 1:3 ratio. 1's ratio to the D and then 3 ratio to the G. So it's this graphene can be found with a 1:3 ratio. This is the highest quality graphene. For the rigid graphene outside and the graphite outside, D band and G band are into the 1:1 ratio. So that's mean they have a lot of functional group. But for the graphite, we cannot see the D band. We just only see the G band because this is a three-dimensional graphite structure, not even in the nature of the graphene's nature. So that is how we can use the Raman spectroscopy to understand the quality of the graphenes. Okay, after that, now we can see how the synthesis, how to characterize. Then what is the application of the graphene? Therefore, so many different applications that we can use, and the range of the supercapacitor, environmental, the gas sensor, catalyst, membrane, bound application, and decoration, and also optoelectronic device, absorber, flexible device, lubricant application. Therefore, a large range of the applications that we can use for the by using the graphene material. And in the market of the derivative the graphenes for the preparation of the graphene derivatives by using the graphene oxide, CVD planes, and also graphene nanoflake. For the graphene oxide, from the chemical process, they can produce a very high quality, not high quality, high mass production, low cost, but very low in quality. But CVD graphenes, the cost is very high. We cannot produce mass production, but they can get a high quality graphene, high purity graphene, something like that. And also the markup fraction of the CVD have only 10%. That graphene oxide used in the widely weights graphene nanoflake can be used at a very large range in the applications. And also in the application of the one specific fee, so for the composites, the graphene nanoflake can be used widely, but CVD is I'm not going to use in the composite because it's a very high quality and also high production cost. So the CVD flame is mostly used in the conductive flame and also in the transistor, the energy harvesting application. So now I'm giving the very general information about the graphenes and derivatives, its structure, synthesis and property, and also the application too. So I hope you enjoyed it. I hope you will get the general knowledge about the graphenes and about the synthesis process, the structure process, the property of the graphene, and also the application, and also how the graphene derivatives is used in the markets too. I hope you enjoy this special session, and then see you again in the next sessions. Bye bye.